to a course on calculus for several real variables. In this lecture, we are going to talk about the extreme values and saddle points. That is the concept of maxima and minima of functions of two variables. Okay, we initially see this concept for a two variable case, and the ideology of how it can be extended to a several variables will be dealt in the upcoming video. So here, uh, okay, let me give you the ideology that we have seen in the one variable case. That is, we'll be given with some function. So if we are given some function, then we'll find the critical points by equating the first derivative to 0, and this will contribute us some points, and those points we call it as critical points. And then we find the second derivative and evaluate the second derivative at this points and see whether this is positive or negative. If it is positive, then your xi is minima, and in this case, if this is negative quantity, then your xi is maxima for these values of, okay, let me write them as xi and xj. The corresponding value of the function when x is xi is called as the minimum value of the function, and this is called as the maximum value of the function. And suppose you have a graph like this. Okay, supposing you have a graph like this, and here, uh, when you equate your first derivative to 0, you are going to get some points, and those points are the points in which you have these peak things. Okay, I think if I do it in another color, you can better understand. So in this point you have a peak, in this point you have a peak here, here, and somewhere here. Okay, at these points your derivative is going to be 0. Okay, so from this, what can we identify? What can be considered as the maximum value of the function? Yes, there are two concepts, that is local extreme points. So when I say extreme points, it means both maximum and minimum, and absolute extreme points. Okay, your absolute extreme points of a function are unique values. So of a function that I'm meaning, so which means I'm talking about the value of f of x, not the value of x. For different values of x, you may get absolute extreme points. For example, if you take y to be equal to sine x or cos x, okay, your the maximum value of this function is 1, and the minimum value is -1, and this 1 and -1 occurs at several values of x. Okay, but your absolute extreme value is 1 and -1. These are unique values, whereas your local extreme points need not be unique one, because around somewhere at a point, okay, the corresponding x value here is this one, right? So you take some neighborhood, that is, if it is in one variable case, you take a very small segment around it. In that segment, that is going to be the maximum value. In this case, we call that as the local maximum. The similar ideology can be extended for the minimum case as well, as we have this local extreme and absolute extreme, and this local extreme is also called as relative extreme points. Okay, so the same ideologies can be extended for two variable case as well, for which you see. So first of all, what do we mean by a local maximum? That is given in this statement. Okay, a function evaluated at the point AB is called as local maximum of the function if this condition holds for all domain points xy in the open disk centered at a comma b. So here we are talking about a center. If suppose this is my point AB, I will have to identify some disk around it. So now let me show you the projections. Okay, let me show you the things in two dimension. Sorry, three dimension. So you have your point AB inside it, okay, around which you have chosen an open disk, okay, some open disk. suppose your function attains a peak at this point, okay, then you call this as the local maximum, okay, and somewhere else it may go to another peak, okay, but in this neighborhood, okay, if you see only around this disk, the point AB gives you the maximum value of the function, and that is why it is called as local maximum. The similar ideology is extended for the minimum as well. Okay, as I said you, for the one variable case, this local extrema are also called as relative extrema. Here, you are given some diagram, and here you may very well see that around this area. Okay, if this is in the three-dimensional case, if you extend, okay, if you see what is the domain, you have identified some region over it. So in this disk, this is the maximum value, and this is why this is called as local maximum. But you are able to identify a value which is bigger than this as well, but that is somewhere in the another disk, okay, and similarly this is the local minimum value, right? So how to find out the local maximum and local minimum, and there are so many examples are given in in this textbook that you can refer. uh, so the first derivative test, that is, here you are given a function of two variables. Whenever you are given a function of two variables, you will have to identify the partial derivatives with respect to x and with respect to y, and equate them to 0. Okay, identify these things. Okay, from this identify these things and equate your del z upon del x to 0 and del z upon del y to 0, or you may simply say them as fx and fy. Equate them to 0 and identify the possible values of x and y, and that points will be the critical points. Okay, actually in this theorem that tells you that if your function has a local maximum or minimum value at some point, at those points your derivative value would be 0. Okay, so just by finding the derivative and equating them to 0 and solving them does not guarantee you that those points will give you the local maximum or minimum. But if the condition is not satisfied, then it cannot be local maximum or minimum. Okay, just kindly note my wordings very clearly. If you have a local maximum or minimum at some point, at those points your derivative will be 0. Okay, in the other words, if the derivative cannot be 0 at some point, that point cannot be a local maximum or minimum. So you are from the infinite number of points, you are restricting yourself to some points where those points can be local maximum or minimum. Okay, we are not giving any assurance that those points will be local maximum or minimum, right? So moving further, uh, exactly the same ideologies that we have seen in one variable case is extended to the two variable case. First, you identified first derivatives and equated them to 0. That's fine. Okay. And suppose the function has a local maximum at a particular point means that we will have to identify some value. So let me call that value as D. That is determinant of fxx, fxy, fyx, fyy. So here we are talking about the continuous functions. So xy and yx are same. This will give you fxx, fyy minus fy, fxy squared. So if the d value is positive and fxx is also positive, then here we are not talking the generalized values. This d has to be evaluated at some point ab. So correspondingly, if it has to be evaluated at some point AB means your second derivative with respect to x and second derivative with respect to y, and the mixed derivative has to be evaluated at this point. If this is 0, then your AB is local minimum. Okay, if d is positive and your second derivative with respect to x is negative means AB is local maximum. If your d is negative, then AB is saddle point. What if d is 0? With this test, you cannot come to any conclusion. So that is what is given in this. So this is the expression d is called as discriminant or Hessian of f. Okay. So now let us get into some problems. Find the local extreme values of the function. Some function is given and we are asked to find out the local extreme values. So from that function, if you identify what is your del f upon del x, that is your fx, it is going to be y minus 2x minus 2. Okay, del f upon del y, that is your fy is going to be x minus 2y minus 2. And now we will have to equate them to 0. So when you equate them to 0, you are going to get y minus 2x is 2 and x minus 2y is again 2. So if you multiply this one with 2, you would get minus 2x plus 2, minus 4x plus 2y equals 4. And here we have x minus 2y equals 2. And when you add these two quantities, your 2y gets cancelled, minus 3x equals 6. Therefore, x is equal to minus 2. So if you plug in your x is equal to minus 2 in any of these quantities, so minus 2y equals 2. Therefore, minus 2y will be 2 plus 2, that is going to be 4. Therefore, your y is minus 2. Therefore, this contributes you the point xy is minus 2 comma 2. Okay, this is the only point where a function may take extreme value. Now we find the second derivative of these functions from this. So from this my fxx is going to be minus 2 and fyy is also going to be minus 2 and my fxy. So this one I am differentiating with respect to y and I am getting 1. Okay, therefore now my fxx minus fyy minus fxy whole squared is minus 2 multiplied with minus 2 minus 1, which is 4 minus 1, that is 3, which is positive. Here my d value is positive and my fxx, whether I substitute this minus 2 comma 2 or not, because those are constants, so there is no need of substituting this point and see what is happening. Even if I substitute these points, I am going to get those values only. And my fxx is negative. Hence, we conclude that the function the function attains its local maximum when the value is minus 2 comma 2, right? So that is the conclusion, and the local maximum value is, if you substitute minus 2 comma 2 and see what is happening, it is minus 2 multiplied with minus. Okay, I think I can directly write down the values. It is 4 minus 4 minus 4 plus 4 plus 4 plus 4. So minus 4 cancel with this one and the value is 8. So the maximum value is 8. Okay, here we have another problem. Here we are asked to find out the local extreme values of the same of some function. Here if you find out what is your del f upon del x, it is going to be a minus 6x plus 6y and del f upon del y is 6y minus 8y squared, sorry, 6y squared plus 6x. Okay, if you equate this to 0, this gives you your 6x is 6y. Therefore, your x and y are same. If you substitute your x and y are same in this, what would you get? You would get uh, minus 6y square plus 12y equals 0. And from this, of course, what you can take the y outside. You can take y outside, or if you want you can take minus y outside. So it's gonna be 6y minus 12 equals 0. So from this what you get is your y is 0 and y is 2. These are the 2 points that we get out of these things. Okay, when we get these two things, your x and y combination can be either 0 0 or 2 comma 2. So these two are the points that we can get out of these things. I think there is some mismatch in the page. 805 and we have 804. Oh, yeah. So these are these are the two critical points that we have got out of these things. Fine. And we'll have to find out the second derivatives. So I think I can complete this problem somewhere here itself. Hope you people can follow. If you find your second derivative from this, that is minus 6, and from this it is going to be what, 6 minus 12y, and fxy is 6. And if you see what is happening with this, your d is fxx fyy minus fxy squared, which is minus 6, or you may write this as 6 multiplied with 12y minus 6 minus 36. Okay, now we'll have to evaluate this d at 0 0. If you evaluate this at 0 0, you are going to get minus 36, which is minus 72, which is negative. In this case 0 comma 0 is saddle point. Okay, next is d 2 comma 2. So it is 6, 24 minus 6 minus 36. That is 6 multiplied with 18 minus 36. So it is 108 minus 36. Anyway, this is some positive quantity. So here you get d of 2 comma 2 is positive, and your fxx, which is minus 6, which is negative. Therefore 2 comma 2 gives local maximum, and the local maximum value is f of 2 comma 2, which is 3 multiplied with 4, that is 12, minus 2 cube is 8, 8 with 2 is 16, and this is 4, 4 with 3 is 12, and plus this is 2 times of 2 4, 4 times of 6 is 24. So 12 and 12 gets cancelled. 24 minus 16 is going to be 8. So in this case also we are getting the maximum value is 8. Okay, if you try to plot this function with the help of some computer tool, you can very well see this is gonna be the graph of the function. Okay, and in between we missed some page. Just a minute, let me 803, and directly we have gone to 805. In between we have some page 804 that is given here. A point is said to be a critical point. Okay, so the definition of critical point is given here. If your both del f upon del x and del f upon del y, if both are equal to 0 at some point, then those points are called as critical points. Or sometimes your derivatives del f upon del y, del f upon del x and del f upon del y do not exist even. Either this must happen or this must happen. So these are happening at some points. Those points we call it as critical points. Okay. Here in the second derivative test, we have said something called a saddle point. A saddle point means uh, where you cannot come to any conclusion. That is, if your discriminant is less than 0, we call that as a saddle point, which means about the point itself, about the in the neighborhood itself, that is over the disk, you may see your function behaves both this way. Some points is behaving this way and some points is behaving this way. That is why we cannot come to a conclusion that whether this gives us a maximum value or minimum value, and those points are called as saddle points. And here we have few examples that I think you people can work out. I have given you some enough examples, the ideologies how to work out these problems. That is why you can very well find these things. And this is a good example where you don't get any maximum value or minimum value. Okay, so let me uh, just tell you how it is to be done. If you find del f upon del x, just a minute, I think I don't know why it is happening like this. Sometimes it is like this only. Okay, so your fx, the first derivative is with respect to x is minus 2x, and your fy is 2y. If you equate them to 0, you can see this is the only point. Okay, and this is the only point where your fx and fy can be 0. Now if you take the case that is along y-axis, if you take along y-axis, there your x value is 0, therefore your function becomes what? Only y squared. So this becomes the functions of y alone. Therefore let me take this as some function of y, and if I try to find out the first derivative and do the things, okay, this function is a non-negative valued function. Here I can find only minimum value. I cannot find out maximum value because I don't have any restrictions over this x and y. Similarly, if I take along x-axis, that is when my y is 0, I get my function is becoming minus x squared. So this function is a non-positive function. Here I can find only the maximum value, not the minimum value. But when I combine these two things, there comes the problem. Because one function cannot possess any minimum value and the other function cannot possess any maximum value. When I combine these two things, it cannot give me either maximum or minimum. So the point 0 comma 0 here is a saddle point. Okay, now back to the discussion. Here we have absolute next concept, that is absolute maxima and minima on closed bounded regions. So which means till now we were given only the function. Okay, here the domain may also be specified. Domain or some region may also be specified. Okay, so what is different from local maxima and absolute maxima? Local maxima is about some locality. Okay, over some point or over some disk. If it is a maximum value, then it is local maximum, and this aim goes for minimum as well. Absolute means over the entire region we will have to identify all possible local maximas, as well as we'll have to evaluate the function at the corner points, that is on the boundary as well. We will have to identify the value of the function. So among these all local maximas and the points and the values on the boundary, we will have to identify the maximum value. Maximum among these maximum, that is going to be the absolute maximum. Similarly, we will have to identify all local minimum points, and we'll have to evaluate the function at the boundary points as well. So among these minimum values and the points on the boundary, the most minimum is called as the absolute minimum. Okay, so here we have an example. Here we are asked to find out the absolute maximum and minimum of this function on a triangular region bounded by x is equal to 0, y is equal to 0, and y is equal to 9 minus x. So if you find out your things, that is what? If you find out your triangular region, x is this is the line y is x axis, your y is 0, and y axis is x is 0. And if you give x is equal to 0, you will get x0 means you will get 0 comma 9, this point. And if you give y is equal to 0, you will get x is equal to 9 and this point. So look, joining these two lines, you get your triangular region completely done here. So in this region, now first we will have to identify the maximum and minimum, that is the local maximum and local minimum at interior points, for which we will have to differentiate the given function with respect to x, and this gives me 2 minus 2x, and del f upon del y is again 2 minus 2y, and if I equate them to 0, this gives me x is equal to 1 and this gives me y is equal to 1. So the 1 comma 1, this is the point that is contributed by the first derivative. Okay, here I don't need to go for the second derivative test and all. If needed, yes, of course we may go, whether to verify whether this is a local maxima or minimum. Here you just evaluate your function at this point, or initially you just find this point 1 comma 1. Now we will have to check the happenings on the boundary. So here the triangle is named with the corner points O, A and B. So now let me check on OA. On OA my y value is 0. Okay, my y value is 0, therefore my f of xy, in this f of xy I'll have to substitute 0. Therefore it becomes 2 plus 2x minus x squared. Now we may treat this as a function of one variable, and you do your usual calculations that we do for one variable thing. That is, you find df upon dx, and that happens to be 2 minus 2x, and if you equate this to 0, you get x is equal to 1. So x is equal to 1 comma 0. The point is plotted here. Okay, and similarly you will have to do what? Uh, then if you look on the OB, there your x value is 0, therefore f of 0 comma y is going to be 2 plus 2y minus y square. Here also you'll have to do df upon dy, and that is 2 minus 2y. If you equate this to 0, you get y is equal to 1. Therefore 0 comma 1, the other point. Okay, this is the point that we have already found. And what? Now along this line AB, along this line we know that your y value is 9 minus x. So f of x comma 9 minus x. So this becomes what? 2 plus 2x plus 2 times of 9 minus x minus x squared minus 9 minus x squared. Now this becomes the functions of x alone, and if you find what is df upon dx, so this is going to be 2 minus 2 minus 2x minus 2 times of 9 minus x with minus 1. Okay, so 2 and 2 gets cancelled. It is minus 2x minus 18 plus 2x. Actually, we have minus, so when it comes before, you will have plus here and minus here. Yeah, so this minus 1 multiplied with minus 2 becomes plus 2. So 2 into 9 is 18. 2 times of minus x is minus 2x. So this is minus 4x plus 18. If you equate this to 0 and solve for x, you will get 18 upon 4, which is 9 upon 2. So you have your y to be 9 minus x. In this, 9 minus 9 upon 2 is going to be 9 upon 2. So you get a point 9 upon 2 comma 9 upon 2. So that is what we have here. Okay. So after finding these points on each line, now we will have to consider the corner points as well. Generally at corner points we may get a maximum or minimum. So we include the corner points as well. Now we have all these points, right? So with all these points, what should we do is that just try to make a table. I don't know if it is okay. Let me give you function value. Yeah. So the points, what are those points? That is 0 0, 0 1, 1 0, 1 1, 9 0 0 9, and 9 upon 2 comma 9 upon 2. Now at all these points you will have to evaluate your function value. That is 2 plus 2x plus 2y minus x squared minus 2y. Sorry, minus y squared. I think that's it. Yeah. So this is our function. We'll have to evaluate at these points. So here we are going to get 2. It is actually 2 plus 0 plus 0 minus 0 minus 0, which is 2. Here we'll get 2 plus 0 plus 2 minus 0 minus 1. So it is going to be 3. And here 2 plus 2 plus 0 minus 1 minus 0, which is again 3. So 2 plus 2 plus 2 minus 1 minus 1, 6 minus 2, which is 4. When we substitute 9, we are going to get 2 plus 18 plus 0 minus 81 minus 0. So it is 20 minus 81, which is minus 61. So if I substitute this also, I am going to get 2 plus 0 plus 18 minus 0 minus 81. It is again minus 61. And when I substitute 9 upon 2, it is 2 plus 9 plus 9 minus 81 upon 4 minus 81 upon 4. So I can see it is 18 plus 20, 20 minus 81 upon 2. So it is 40 minus 81 upon 2, that is minus 41 upon 2, that is minus 20.5. So among all these, you will have to choose the maximum value among it. So the maximum value among it is 4 and the minimum value among it is minus 61. So your absolute maximum is 4 and it occurs at 1 comma 1, and absolute minimum is minus 61 and that occurred at 9 comma 0 and 0 comma 9. Okay, so this is how we'll have to work out and find out the absolute maximum and absolute minimum. Okay, and here we have some practical kind of an example. So to solve these kind of problems, we use the method of Lagrange multipliers. That is to be seen in the next lecture only, but still using some direct methods also we are able to find out the calculations, and that is explained in this problem. Here a delivery company accepts only rectangular boxes. Okay, I think I should go with this. Okay, only the rectangular boxes is accepted by the delivery company. That rectangular box must be of the given specification, that is the sum of length and girth do not exceed 108 inch. So the girth is the perimeter of a cross section. Okay, girth means perimeter of the cross section, the one that is specified in some different color in the diagram, okay, that you can see. Okay, suppose x, y, and z represents the length, width, and girth. Then the girth is 2 times of, okay, just a minute. Yeah, this is, if this is y, then this is y, and this is y. This is z, and this is also z. So therefore, your girth is the perimeter of this rectangle. That is y plus z plus y plus z. That is 2y plus z. 2y plus 2z. So that is the girth. And it is given that the sum of length and width must not exceed 108 inch. So it has to be maximum of this quantity. Okay, and we'll have to identify the dimensions of the largest volume. So the volume, we'll have to maximize the volume, that is our objective. So the volume is given by xyz. So now we'll change this to a function of only two variables from this one. So we have x plus 2y plus 2z equals 108. So from this your x is 108 minus 2y minus 2z. Okay, so if we substitute that one into it and make some simplifications, you get this one. and we differentiate this one with respect to y and then with respect to z and equate this to 0. So equating this to 0, from these what we get is either z is equal to 0 or 4y plus 2z equals 108. This is another possibility. The other one is y is equal to 0 or 2y plus 4z equals 108. So from this, now we'll have to do the calculation and find out the possible values. So that is the first case. Z is equal to 0 and y is equal to 0. Either I may take this one and this one. Completely fine. And I take z is equal to 0 and 2y plus 4z is equal to 0. So if you plug in z is equal to 0, you get, 108. It is equal to 108. So when you give z is equal to 0, then this contributes y is equal to 54. Okay. And similarly, if you take 4y plus 2z is equal to 0 and y is equal to 0 from the second, and if you give y is equal to 0 into it, this gives you z is equal to 54. So from the first one we get 0 comma 0, from the second one we get 0 comma 54 comma 0, because y comma z is the thing that we are talking, 0 comma 54. And finally, if you consider 4y plus 2z is equal to 108 and 2y plus 4z is equal to 108. So if you solve these two things, that is, let me multiply the first equation by 2 and I see 8y plus 4z is equal to 216, and this is 2y plus 4z equals 108, and if I subtract these two things I get 6y is equal to 108. So from which my y is equal to 108 upon 6, that turns to be 18. So when I give y is equal to 18 in any of these equations, okay, if I given the first one, 4 times of 18 plus 2z equals 108. So it is 72. So 2z is equal to 108 minus 72. That happens to be 36. Therefore, my z value is 18. So this contributes the point 18 comma 18. Now I have these four coordinates. So with this four coordinates, now I'll have to see what is actually happening. Here we are trying to maximize the volume of a box, right? So among these 4 points, if you consider 0 comma 0, then your volume is going to be 0. 0 comma 54 also makes the volume to be 0. 54 comma 0 also makes the volume to be 0. That cannot happen. That cannot be the maximum value. So 18 comma 18 is the only point which may give you the maximum value, for which we apply the second derivative test. That is, we find vyy and vzz and vyz also, and we substitute this 18 comma 18 points into these quantities and see this discriminant value. Actually we have, here they have found the discriminant value for the general case and substituted this point, and see that is a positive one. Here the first variable is y, and that is why they have checked it for y, and that is happening to be negative. Therefore we come to a conclusion that this point gives us the maximum value, that is the maximum value. So that is happening when y is 18, z is 18, and we'll have to identify x also, that is 108 minus 2y minus 2z. So 36 minus 36, so it is 108 minus 72 is separated, therefore we are going to get what? 36. So when x is 36 inch, y is 18 inch and z is 18 inch, we get the maximum value. And if you just multiply all these quantities, you get 11,664 inch cube is the volume. If you convert that to feet, you are going to get 6.75 feet cube. So, and this is the summary that we have seen in this lecture that you can go through. Thank you.